All right, guys. Good morning. Good morning. Welcome. Almost to the end of the month here. Hope everyone's doing well, staying safe, keeping all right. We've got paired t-tests for the differences in paired data as our focus this week. Looking at our course calendar here, I got a quiz planned for tomorrow, as well as next Thursday, May 7th, on chi-square goodness of fit testing for categorical variables, and then our end of course assessment on Thursday, May 14th. If any of those dates for those assessments don't work for you, please communicate that with me because I need to have everything done as soon as possible on the 14th in order to give you your grade. If you want to do anything after the 14th, the answer is going to be no, because I have to get my grades reported to DMAC in a timely manner, and they have a deadline. So if there's anything that needs to be done, that's kind of the end of the road there. That's going to be a problem, and you want to take any quiz or that end of course assessment early so that you're good to go. We can get that scheduled. Any questions on that, or I guess any questions in general? I'd be happy to go over any problems or questions you guys are working through before I get into what I had planned for this morning.
Mr. Hanson, I did want to ask, so per se that we didn't get reassessments done, and we show that we know how to do it on the course final, will that make up for it?
No, you'd need to reassess.
Okay.
Okay, for our quiz tomorrow, it's going to be over hypothesis testing for the differences in two means and paired t-tests and confidence intervals. I sent out a study guide earlier this week. I have a few more examples on paired t-tests this morning to work through with you if we have time, but were there any questions off of this before we go any further? This study guide specifically, or any practice problems in general? Okay, hearing no questions, let's look at some more examples of paired t-tests. We're going to use that same spreadsheet that I had linked from class on Monday. You can find the link to that spreadsheet on this little tab in our Google Meet page. Once you click on that, it'll ask you to make a copy, and it has the same data spreadsheet that we're going to use for some questions this morning. All right, so looking at inference on paired data. Paired data is different than two means hypothesis testing and confidence intervals because rather than sampling from two different populations, I'm sampling the same population twice. And we're creating inference for differences in those two paired samples. I'm taking two sets of data and I'm making it into one set of paired differences and conducting statistical inference from there. Kind of what this little text box up here talks about. Comparing two population means where we have two samples in which one sample is paired with observations from the other, thus paired. We're taking two samples from the same population, thereby creating one set of data of paired differences. So noteworthy formulas for confidence intervals and hypothesis testing statistics for paired data. This D bar just like X bar is the sample mean, D bar is the mean of the paired differences. And S sub D, right there, S sub D is the standard deviation of the paired differences. This is just the same slide from class on Monday. So hopefully you've seen this before. Let's look at a couple questions. So we're going to take a sample of different people and record their pulse rates in beats per minute from when they're sitting and standing. At the 5% significance level, does standing increase your heart rate? I have this spreadsheet on this document here. Go ahead and select the pulse rate tab in green down below, and we've got the same set of data. Looks like we're looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. No, I'm sorry, pardon me, I overcounted, 15. 15. We sampled 15 people, recorded their pulse rates from either sitting or standing. Let's go ahead and get our statistics for this by creating the differences. Does standing increase your overall heart rate? Now, what you can do is either do sitting minus standing or standing minus sitting. Since what we're testing for is standing increasing your overall heart rate, I want to keep this as easy as possible. So I want these differences to be positive. Let's assume that standing increases your overall heart rate. And when I create the differences, I'm going to go standing minus sitting. And I can see a difference of 5. For this person sampled, their heart rate increased by 5 beats per minute for when they were standing up. Creating my tab, pulling this down. I can calculate all these paired differences. This person, their difference was -2, so their heart rate actually decreased by 2 beats per minute for when they were standing. This person, I don't know what's going on here. They lowered their heart rate 8 beats per minute by simply standing up. When the difference is 0, there was no change in their overall heart rate for sitting versus standing. I did standing minus sitting. You could have done it the other way around. You just have the opposite differences. We'll need our statistics, so equals average. Since this is paired data, let's find the average of these paired differences. Looks like 0.667 for D bar. So it looks like standing from our sample raises your overall heart rate in beats per minute by 0.67. We have some standard deviation here. Of 3.754 beats per minute. Okay, we're going to do 2 different things with this set of data. We're going to do a hypothesis test and a confidence interval for the difference in heart rates standing versus sitting. So let's set up our hypothesis test. We'll need the null hypothesis and the alternative hypothesis. We're testing to see if standing increases your overall heart rate. If standing increases your heart rate, wouldn't the average difference be greater than 0? As I've set it up. If you did sitting minus standing, it would be less than 0. If there was no difference in heart rate, the mean difference would be equal to 0. If we draw the t-distribution here, we have a one-tailed, upper-tailed t-test. For our cutoff t-score, one-tailed 5% significance level puts us in the second column from the left. We had 15 different people, so 15 minus 1, 14 degrees of freedom. I see a t-score of 1.761. If we can calculate based off of our sample a t-score that's more extreme than this, we have significant results. And t equals, from our notes, d bar divided by s sub d over the square root of n. So our t-score is 0.667 divided by, what was it again? 3.754. Over the square root of 15. So I see a t-score of 0.6881. Based off of this t-score, what should our decision be? Compare that back to our rejection region with this cutoff from the previous slide. Are we more extreme, greater than 1.761? Our t-score lies closer to 0, to the left. So I would think that we need to fail to reject. We lack evidence that standing increases heart rate in beats per minute when compared to sitting. And as a final wrap up for this hypothesis test, let's calculate the p-value. We'll need Google Sheets. And in some blank cell, type equals tdist. To type into Google Sheets, we need the t-score from our sample, the degrees of freedom, and the number of tails in our hypothesis test. So our test statistic was 0.6881. We had 14 degrees of freedom and a one-tailed hypothesis test. So our p-value is 0.2513. So in context, that p-value tells us that if there really was no difference, if the null hypothesis was true, if there really was no difference in heart rates for sitting and standing, we would find 15 people with their data such as ours 25% of the time. So any difference is just normal variability. We lack evidence to show that standing increases your heart rate. Any problems there? Okay. If you go to the Celery diet tab, oh, I'm sorry, we had to do our confidence interval next. Getting ahead of myself. Let's do our confidence interval next. Confidence interval is d bar plus or minus t-score times the standard error of s sub d over the square root of n. D bar was 0.667 plus or minus some t-score. So what t-score do we need? We're doing, I think, a 95% confidence interval. Yep. So 95% means that there's 2.5 in either tail. You can find that t-score on sheets using t.inv. We need the probability with the degrees of freedom. So we had, for the top one, 0.975 to the left of that top t-score, 95 in the middle, 2.5 in the tail, with 14 degrees of freedom. Gives me a t-score of 2.1447. Or on your t-table, 95% confidence level is the middle column. 14 degrees of freedom is about 2.145. Standard deviation was 3.754. Over the square root of 15. So let's go to the calculator and get this typed in. 2.145 times 3.754, the square root of 15. It gives me a margin of error of 2.079. So our estimate of 0.667 beats per minute is no more than 2.079 beats per minute away from the true difference for heart rates in sitting versus standing. So let's create our final confidence interval. 0.667 minus that previous margin of error, negative 1.412. Change this to plus 2.746. Because this confidence interval is neither strictly positive nor strictly negative, because 0 is in the interval, we can't really be sure if there is a difference in heart rates between sitting and standing, which is why we failed to reject the null hypothesis earlier. As an interpretation, we are 95% confident that on average, heart rates for standing are between 1.412 beats per minute less to 2.746 beats per minute more than when sitting. Questions, guys? Okay, tell you what. Got about half the class left. Why don't you guys try the celery diet? Question in the next tab over. Many people believe that eating celery has substantial health benefits. 10 people are randomly chosen to eat celery every day for a week and track their weight. Does eating celery every day for a week make people lose weight? At a significance level, a type 1 error probability of 1%. Also write a 99% confidence interval. I'm going to give you guys about 3 or 4 minutes head start, and I'll kind of work behind you here so that you can check your work as we go. Does that make sense? Okay. If there's no questions, I'll start working at about 11:30. If you have any problems, go ahead and take yourself off mute and speak up. I'd be happy to help. Person 1 lost 5 pounds as a result of eating celery for a week. Sliding this tab down. I see a lot of negative numbers. Looks like eating celery might cause you to lose weight. Lots of variability, though. 4.624 standard deviation pounds. Some people lost a lot, some people didn't lose a whole lot, maybe even gained. All right, I got about 11:30 here, bottom of the hour. I'm going to start working through this. Hopefully, many of you have already gotten a little bit of a jump start on me. If you have any questions as I kind of work through it on my own, please speak up. I'd be happy to answer any questions that you're having. Our sample average for the paired differences was 5.6 pounds lost, negative 5.6, with a standard deviation variance of 4.624 pounds. We're testing to see if eating celery every day makes people lose weight. So for our null and alternative hypothesis, let's assume that there is no difference for eating celery and losing weight. Therefore, these mean differences would be 0. And then for our alternative, we're testing to see if people lose weight. Therefore, the differences would be negative, less than 0. We're testing at the 1% significance level. I want to reject a true null hypothesis only 1% of the time as my allotted error. So that t-score, 1% puts me in the second column from the right for 9 degrees of freedom, about 2.821. Of course, you can get the same thing on sheets. Using t.inv. All right, so our test statistic. Ooh, I'm sorry. I put this in the wrong place. We have a lowered tailed test. So we're using the right tail. Negative 2.821. All right, our t-score for the sample is negative 5.6 divided by 4.624 over root 10. Gives me negative 3.83 if I round up. So therefore, we should reject the null hypothesis. Our evidence suggests that eating celery every day causes people to lose weight. For our p-value, we'll need sheets again. Our t-score was, one more time, negative 3.83. We'll put positive 3.83 in here. We had, what was it, degrees of freedom next, so 9. And the number of tails would be 1. I see a p-value of 0.002, approximately. If p is low, we reject the hoe. The probability of our sample or sample more extreme is only 0.2%. Hypothesis test part. Any questions here? Okay, let's move on to the confidence interval portion. D bar plus or minus the margin of error, which is our t-score times the standard error of S sub d over square root of n. So negative 5.6 plus or minus the t-score for a 99% confidence interval puts me in this last column. 9 degrees of freedom is 3.250. Times our standard deviation, which was 4.624 over root 10. All right, let's get the margin of error calculated. 3.25 times standard error. So 4.752 pounds is our margin of error. What was that one more time? I just forgot. 4.752. So our average difference is 5.6 pounds is no more than 4.752 pounds from the actual difference in weight from eating celery for a week. So let's figure out our confidence interval by taking negative 5.6 minus the margin of error, negative 10.352. And then negative 0.848. And this would be measured in pounds. Since our confidence interval is strictly negative, we can be certain that eating celery causes weight loss, which is why we rejected the null hypothesis in the previous part. As an interpretation, we are 99% confident that eating celery every day causes people to lose between, what was it, 10.352 pounds and 0.848 pounds on average. Paired samples. You're doing statistical inference on the paired differences rather than statistical inference on two sets of data from sampling two different populations. Differences from two different populations. Questions, guys? Hopefully you worked through that and got roughly the same values. Were there any other questions that I can answer now? Practice problems, review guide, anything else that might cause you some concern before your quiz tomorrow morning? Okay, if not, I think we'll call it good there. If you have any problems between now and tomorrow for the quiz, feel free to shoot me an email. We can do a video call and work through some questions together if you'd like. And I'll see y'all guys same time, same place tomorrow for your quiz. Have a good rest of your day.